Okay, let's talk the physics of ventilation. And recall the definition of ventilation in this case is airflow into and out of the lungs. If we're dealing with alveolar ventilation, we're referring to airflow into and out of the alveoli. Regardless of what we're referring to, whether we're talking about the total lung volume or total lung compartment versus just the alveolar compartment, the reality is the physics are the same. Gas is a fluid, and like all fluids, it's going to flow from high pressure to low pressure. High pressure to low pressure. You can compare mentally gas to water. Now they're slightly different. Their physics are slightly different. Both water and gas are a fluid, but water is also classified as a liquid. So the molecules in water are less free to move. They stay together as a group because of those hydrogen bonds and because of the nature of the liquid. Whereas gas molecules can bounce all over and they are free to fill the entire volume of their container, whatever that container happens to be. Nevertheless, it also often helps mentally to think about the way water flows because we tend to understand that a little bit more intuitively. Water's always going to flow downhill from high pressure to low pressure. So if you're looking at water pressure in your shower, for example, as you open the faucet, the water comes out of the spigot and into the tub or the shower. And it's moving from high pressure to low pressure. The more pressure you have, the stronger the flow of water. And that's true with the gas. The more difference in pressure that you have, the stronger or faster the air is going to move. Pressure differences are created between the ends of the two conducting zones, and by end I mean the end one would be your nose, right? Your nasal cavity. And then the last portion of the conducting zone would be those terminal bronchioles, right? And there's a difference in pressure there created by changes in volume in the lungs. And that's something that's really important that you understand, that these pressure differences are created due to volume changes. Now I'm going to change the order of my slides a little bit from what you have posted in Canvas, because after doing this a couple times and practicing it and deleting it, I decided it's a little better to do it in this order. So just bear with me. The movement of gas from high pressure to low pressure occurs due to a law called Boyle's law. Boyle's law simply states that pressure of a gas is inversely proportional to the volume of its container. If you look at the picture on the right, we have two containers, and both of these would represent an airtight container, and we have a plunger that seals that container, and we can move that plunger up and down. So the first container is this one here, and we're going to look at the volume. The volume is, we're going to pretend that the volume here is 1 liter. And you'll notice that we've got these gas molecules here, and these gas molecules are zipping around in random directions and bouncing off the walls of their container. And as the gas strikes other gas molecules, and as it strikes the containers, it's exerting pressure. That's essentially what the pressure is you can think about it as the number of times you get hit with these gas molecules. In a 1 liter container, the gas has that space, that 1 liter space to move around and zip around in. And so because of that space, maybe the number of strikes are enough to give me 100 millimeters of mercury worth of pressure. Okay. Then if we take this plunger and now we push it down, there's no way in this example for gas to escape. We've suddenly decreased the space, we've cut it in half, but the number of gas molecules are the same. And so if you look at this picture and study this picture, you're going to notice that it's illustrated so that the number of strikes against the walls of the container have increased dramatically. Over here on the left side of the picture, we only had 2 strikes. Over here on the right side of the picture, you'll notice that we've got a number more of hits. So we can look at those hits and 1, 2, 3, 4, 5, 6, 7, plus they're hitting each other. And anyway, my point is that the frequency of collisions increases dramatically because the space is so much smaller. This increases the pressure. And so when we take that volume and we cut it in half, my pressure doubles. We have this relationship, this inverse proportional relationship of pressure and volume. So if we look at this and call this P1, the one on the left, the box on the left is P1 and V1, so pressure 1, volume 1. Box on the right is pressure 2, volume 2. Multiply P1 and V1 and multiply P2 and V2, and they're equal to each other. And you can do that math. 1 times 100 by 1 times 100 is 100. 0.5 times 200 is still 100. And so the volume, that relationship means that you get equivalent values based on how you're altering and changing the pressure and volume relationship. Now in the lungs, it's going to be a little different. The lungs they're not closed containers. We have these airways that can be connected to the atmosphere. So we're going to take a look at this one over here on the left. And imagine now I've got this trachea here. Let's go ahead and draw ourselves a trachea. Okay. And so here's my trachea, we'll pretend. And we'll say that it's connected with the atmosphere. Well, as we decrease the volume of that container, these little guys are going to be striking against the walls, yes, but they're also going to escape. And so we end up with air flowing out of this container. And if we imagine that this was the lungs, we would have exhalation. Okay. And so we're going to be looking at that, and I want you to understand how it is related then to Boyle's law. There are 3 pressures that we're going to be talking about today, and I want you to know them and understand them. The first is atmospheric pressure, and that's fairly straightforward and easy to understand. The second is interpulmonary or interalveolar pressure. Either term is fine, they mean the exact same thing. And the third is this interpleural pressure. Okay, to help you understand, we're going to do a quick series of drawings here. We'll start by defining atmospheric and interpulmonary or interalveolar pressure. If we look at the respiratory system, we've of course have the trachea. There we're going to break into the primary bronchi, which would then branch into secondary bronchi. This is not meant to be anatomically accurate. Tertiary bronchi, and these branches would continue until ultimately we would reach the alveoli. We have, of course, the left and right lungs, like so. Okay. So that's going to represent my left lung. We'll go ahead and draw one in here representing my right lung. Give a space for the heart. Okay, not the most beautiful, not publishable worthy, but it'll do the trick. So here we have the lungs, and we can assume that the trachea is going to be connected to a pharynx and to a nasal cavity, and that nasal cavity provides access to the atmosphere. So out here we're going to have my atmospheric air. Now that atmospheric air is full of gases that are whizzing around and bouncing off things and generating pressure. At sea level, the average pressure that this atmospheric air is generating is 760 millimeters of mercury. I'll elaborate a little bit more on that 760 millimeters of mercury. We're going to get into this a little bit more and what actually is part of atmospheric air when we talk about partial pressures. For right now, that this is going to do the trick. This will work. Okay. At sea level, this is what we've got here. The pressure in the lungs, in the alveolar tissue, okay, is my intra pulmonary, or if we want to refer to just the alveolar sacs, my intra-alveolar pressure. Okay. And that's what's present in the lungs. Now, the intrapleural pressure requires understanding something a little bit more. And I want to give you an analogy to help you to understand this. I want you to think about a water balloon. So we're going to take this water balloon and we're going to fill it up with water, but we're not going to fill it up all the way. Okay? And we're going to tie it off. So this water balloon is tied off up here. Okay? And that's my water balloon. It looks kind of like a chicken leg. Whoops, didn't mean to erase the whole thing, but anyway. Okay, so here's my water balloon. Kind of floppy a little bit, but there's still water in it. Okay? Now I want you to imagine taking your fist and putting it into the water balloon so that you are wrapping your fist in your water balloon. And so we're going to have the maybe these are your fingers and your knuckles, and I guess we'll put a thumb there, and we have our little mutated fist right here. Okay. The water balloon, made out of latex, has two surfaces that we're interested in. The surface that touches the fist, okay, I'm going to color that in red. And then we have the other surface, which I'm going to color in blue. Okay, the other surface here. Now notice that even though there's two different surfaces, okay, two completely different surfaces, it's still the same balloon. And the latex that makes the balloon is continuous. It's not like we start and we stop anywhere. And there's water that separates the fist from the blue side of the balloon. Okay? The pleural sac works very similar to this, except for the amount of space between the two surfaces is incredibly tiny. Okay, incredibly tiny. We have a very, very thin layer of water in between the two surfaces. The first surface, I'll go ahead and color that in red, is what we call our visceral pleura. Okay, and it's a membrane, and this membrane adheres to the lung tissue. Now I'm only going to draw it on one side, okay, just because I don't want to spend forever on this drawing. Just going to draw it on the one side here. Okay, and so this is my visceral pleura, and it wraps around and it connects with the lung tissue, the visceral pleura. Then we have our parietal pleura, and I'm going to dramatically exaggerate the space between these. Okay, it's not this big at all. It's just a few layers of water molecules. I mean, just, imagine maybe stacking up 3 or 4 water molecules in between this space. It's really very, very, very tiny. But nevertheless, the visceral pleural membrane and the parietal pleural membrane are actually part of this sac that wraps around the lungs. Those membranes are really the same structure. The space in between, this space, filled with a tiny layer of water, teensy tiny layer of water, that space is my interpleural space. Okay, inter as in between. Okay, interpleural space. Okay, and so when we talk about the interpleural pressure, intrapleural pressure, we're referring to the pressure that exists in this layer of fluid. Okay? That pressure that exists in that space is my let's see if I left myself enough room, pleural pressure. Okay? All three of these pressures are very important in terms of how the lung functions. And so we're going to take a close look at these.